You know that most metals are found in nature in a combined state, owing to their high reactivity. Metals found in a combined state in the Earth's crust are known as minerals. Only those minerals that have a relatively high concentration of metal and can be extracted in an easy and cost-effective process are called ores. The only metals found in free or native state are gold and platinum. They are usually found along with earthly or rocky impurities such as sand and clay in the Earth's crust. The relative abundance of metals varies in the Earth's crust. The table here lists the relative abundance of some of the metals in the Earth's crust by weight. Of these, aluminium and iron are relatively more abundant than others. Aluminium constitutes about 8%, while iron constitutes 5.8% by weight of the Earth's crust. Thus, aluminium is the most abundant metal and iron the second most abundant metal by weight in the Earth's crust. Also, aluminium is the third most abundant element and iron the fourth most abundant element by weight of the Earth's crust. The table here lists the principal ores of some important metals and their composition. Both aluminium and iron are used widely in industrialized nations. Naturally occurring aluminium is a major component of silicates such as mica and clay. Aluminium is extracted mainly from its principal ore bauxite, since it is an economically viable source. Valuable gemstones, such as rubies and sapphires, contain aluminium oxides along with traces of transition metals as impurities. Rubies are crystalline forms of aluminium oxide, which are red in color due to the presence of chromium as an impurity. On the other hand, sapphires are available in various shades owing to the presence of impurities such as nickel, cobalt, and titanium. Iron is mainly extracted from its oxide ores, such as hematite and magnetite. The iron extracted from these ores is mostly used in the manufacture of steel, an alloy of iron. Iron is also an essential element found in biological systems. Other metals that are extensively used are copper and zinc. You can see from the table that copper and zinc are extracted from their oxide. Sulfide, or carbonate ores. You already know that most metals are found in nature in a combined state. Metals that are found in a combined state in the Earth's crust are known as minerals. Not all minerals can be used to extract metals. Only the minerals that have a relatively high concentration of metal and can be extracted in an easy and cost-effective manner are used for extraction. Such minerals are known as ores. For example, bauxite is the principal ore of aluminium. The metal is extracted from the ore after a series of procedures and techniques known as extraction and isolation procedures. The main steps involved in the extraction and isolation of metals from ores are given here. Concentration of the ore, isolation of the metal from its concentrated ore, refining of the metal. The branch of science and technology that deals with the isolation of metals from their ores is known as metallurgy. An ore contains a metal associated with other andesite substances like sand, clay, etc. These andesite substances are collectively known as gangue or matrix. The process of separating gangue from an ore is known as concentration of the ore. It is also called dressing or benefaction. Metals can be concentrated from their ores using any of these methods: hydraulic washing, magnetic separation, froth flotation, or leaching. The choice of the technique used for extraction depends upon the differences in the physical properties of the compound of the metal present and that of the gangue, the type of metal, the facilities available, and environmental factors are also taken into consideration. Let's now look at each method in detail. The name hydraulic means operated by the pressure created by forcing water or another liquid. Washing ore with water is known as hydraulic washing. Gold mines make use of the hydraulic washing technique. An upward stream of running water is used to wash powdered ore. The lighter particles of the gangue are washed away and the heavier ore is left behind. This technique separates the gangue from the ore using the difference in their specific gravities. It is, therefore, also known as gravity separation. Magnetic separation is used when either the ore or the impurities in it are magnetic in nature. For example, separating iron from its ore, hematite. In this method, powdered ore is placed on a conveyor belt that moves over magnetic rollers. As the ore passes over the conveyor belt, the magnetic particles are attracted by the magnetic roller. The magnetic particles fall in a container below the roller, while the non-magnetic particles fall in another container that is away from the roller. Froth flotation separates the gangue particles from the ore based on the fact that gangue is wetted by water, while mineral is wetted by oil. The ore is crushed into fine powder and mixed in water. Then, collectors and stabilizers are added to the water. A collector is a substance such as pine oil or a fatty acid which enhances the non-wettability of the ore particles. A stabilizer is a substance like cresol which increases the stability of the froth. The mixture is agitated with the help of a rotating paddle. This draws air into the mixture and froth is generated. The froth is then skimmed off and is dried to recover particles of the ore. This is similar to the technique that separates butter from buttermilk. The froth flotation technique is mostly used for sulfide ores, as they are easily wetted by oil. It is also possible to separate two sulfide ores by simply adjusting the proportion of oil to water. At times, a depressant is used to separate two sulfide ores. A depressant is a substance that selectively prevents one of the ores from entering the froth. For example, if an ore has both zinc sulfide and lead sulfide, sodium cyanide is added as a depressant. It selectively allows only lead sulfide to enter the froth, but not zinc sulfide. Leaching is used when an ore is soluble in a certain suitable solvent. Let us consider the leaching of alumina from the principal ore, bauxite. The impurities associated with bauxite are silica and titanium dioxide. The leaching of alumina involves dissolution of the ore in concentrated sodium hydroxide at 473 to 523 Kelvin and 35 to 36 bar pressure. When the ore is dissolved in concentrated sodium hydroxide, the aluminium oxide reacts with sodium hydroxide and forms soluble sodium aluminate. The aluminate solution is neutralized by passing carbon dioxide gas. This precipitates hydrated aluminium oxide. The hydrated alumina is filtered, dried and heated to 1470 Kelvin to give pure alumina, that is, aluminium oxide. Another example is the leaching of silver or gold with a dilute sodium or potassium cyanide solution in the presence of air. Silver, when treated with dilute sodium cyanide solution in the presence of air, results in the formation of a complex called sodium argentocyanide. This, when treated with zinc, displaces silver from sodium argentocyanide and results in the formation of pure silver. Ores can be concentrated by using any of the four methods: hydraulic washing, magnetic separation, froth flotation, and leaching. Now, let's see how crude metal can be extracted from its concentrated ore. The concentrated ore must be converted into an oxide, which is more suitable for reduction. For example, if we want to obtain crude copper from concentrated copper ore, we should first convert the concentrated copper ore into copper oxide and then reduce copper oxide to obtain crude copper. Thus, the isolation or extraction of a metal from concentrated ore involves two major steps: converting ore into its metal oxide, reducing the metal oxide into the metal. Let's look at each step. Concentrated ore can be converted into its metal oxide either by calcination or by roasting. Let's see how these methods work. Calcination is the process of converting an ore into its oxide by heating it strongly below its melting point in the presence of a limited supply of air. It is usually carried out in a reverberatory furnace, as shown here. This method is commonly used to convert carbonate ores, such as calamine and dolomite, into their oxides. Also, the hydrated ores lose water of crystallization during calcination. When calamine, that is, zinc carbonate, is subjected to calcination, zinc oxide is formed and carbon dioxide is liberated. Similarly, when dolomite, a double salt of calcium carbonate and magnesium carbonate, is calcined, it gives calcium oxide, magnesium oxide and carbon dioxide gas. On the other hand, when hematite is calcined, it loses its water of crystallization, as shown here. The other method for converting an ore into its metal oxide is roasting. Roasting is the process of heating an ore in a furnace with a regular supply of excess air at a temperature below the melting point of the metal. This process is commonly employed for sulfide ores. For example, sphalerite or zinc sulfide is heated at about 850 degrees centigrade to give zinc oxide and sulfur dioxide. Lead sulfide is roasted at about 600 degrees centigrade to give lead oxide and sulfur dioxide. When sulfide ores of copper, like copper pyrites, is subjected to roasting, copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The iron oxide present as an impurity in the form of gangue is removed by adding flux silica. Iron oxide reacts with silica and slags off as iron silicate. Note that the flux added during the metallurgical process combines with gangue to form slag. The slag can be separated more easily than gangue. Roasting or calcination converts an ore into metal oxide and makes it porous. The metal oxide is porous because the volatile impurities are expelled and the moisture is removed during roasting or calcination. Now, the metal oxide is suitable for reduction. The metal oxide is reduced to metal by using a suitable reducing agent. The choice of the reducing agent depends on the reactivity series of the metal. When carbon is used as the reducing agent, it combines with the oxygen of the metal oxide to give metal and carbon monoxide or carbon dioxide. For example, carbon is used to reduce zinc oxide to metallic zinc. In this reaction, carbon monoxide is released. Generally, heating is required for a metal oxide to be reduced to its metal. The temperature at which a metal oxide will get reduced can be predicted based on studies that come under a branch of metallurgy called pyrometallurgy. On the other hand, thermodynamics helps us choose a suitable reducing agent for the reduction of metal oxide. Dynamics helps us understand the variation in temperature required for the thermal reduction of oxides and to predict which element will suit as the reducing agent for a given metal oxide. The Gibbs energy is the most important thermodynamic term here. You already know that for a spontaneous reaction, the change in the Gibbs energy, delta G, must be negative. Delta G for any process at a given temperature is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change, T is the absolute temperature, and delta S is the change in entropy during the reaction. The change in the Gibbs energy when 1 gram molecule of oxygen is used to form oxides of metals can be plotted against temperature. This graphical representation is called an Aims diagram. These plots not only help us determine the relative ease of reducing a given metal oxide to the metal, but also to predict the feasibility of the thermal reduction of an ore. An Aims diagram normally consists of plots of change in the Gibbs energy versus temperature for the formation of oxides. An Aims diagram for oxides has several important features. Let's look at them one by one. The first feature is that the graphs for most metal-to-metal oxide reactions show a positive slope. Consider a reaction such as the formation of an oxide 2M plus O2 gives rise to MO. In this reaction, the entropy or randomness decreases from left to right due to the consumption of gases. Hence, delta S becomes negative. Thus, if the temperature is raised, then T delta S becomes more negative. Since T delta S is subtracted in the equation, delta G becomes less negative. Thus, the free energy change increases with an increase in temperature, and hence, the plots show a positive slope. The second important feature is that the Gibbs energy changes follow a straight line, unless the materials melt or vaporize. The temperature at which such a change occurs is indicated by an increase in the slope on the positive side. For example, the slope of the ZN-ZNO line changes around 800 degrees Celsius. Similarly, the slope of the MG-MGO line changes around 1120 degrees Celsius. The third feature is that when the temperature is raised, a point will be reached where the graph crosses the line delta G is equal to 0. Below this temperature, the free energy of formation of the oxide is negative. So, the oxide is stable. Above this temperature, the free energy of formation of the oxide is positive. The oxide becomes unstable and will decompose into the metal and dioxygen. Another important feature is that any metal will reduce an oxide of another metal that lies above it in an Aiims diagram. Thus, Al reduces FeO, CrO and NiO in the well-known thermite reaction. But Al will not reduce MgO at a temperature below 1500 degrees Celsius. Aiims diagrams also suffer from limitations. One is that they assume that the reactants and products are in equilibrium, which is not often true. Another limitation is that, although they indicate whether a reaction can occur or not, they do not say anything about the rate of the reaction. The change in Gibbs free energy of a reaction, delta G, is a measure of the thermodynamic driving force that makes the reaction occur. For a spontaneous process, delta G is negative, while a positive value of delta G indicates a non-spontaneous process. It can be seen that for a reaction where change in entropy delta S is positive, the reaction is spontaneous at a sufficiently high temperature as the magnitude of T delta S exceeds delta H. If the reactants are in equilibrium with the products, the change in Gibbs free energy can also be expressed in terms of equilibrium constant K. With the help of the equation, delta G is equal to minus RT natural log K. As you can see, in this equation, delta G can be negative only if K is positive. This can happen if the reaction proceeds in the forward direction, that is, the reactants combine to give the products. It is important to note that two independent reactions can be coupled and are feasible, provided the overall delta G of the two reactions is negative. This coupling is particularly useful for the reduction of oxides of elements. In metallurgy, a metal oxide is reduced with a reducing agent. During reduction, the metal oxide decomposes as shown here. MXO decomposes to give XM plus half O2. The liberated oxygen is taken up by the reducing agent. If carbon and carbon monoxide are used as reducing agents, then the reaction can be represented as C plus half O2 gives CO. CO plus half O2 gives CO2. And half C plus half O2 gives half CO2. As you can see, the second reaction represents the incomplete oxidation of carbon, while the fourth reaction represents the complete oxidation of carbon. The reduction of a metal oxide can thus be represented as MXO plus C gives XM plus CO, or MXO plus CO gives XM plus CO2, or MXO plus half C gives XM plus half CO2. As you can see, overall reaction 5 is the sum of reactions 1 and 2. Reaction 6 is the sum of reactions 1 and 3. And reaction 7 is the sum of reactions 1 and 4. Now, if the overall value of delta G is negative for these coupled reactions, then the reaction will be feasible. As discussed, a sufficiently high temperature favors negative delta G. The position of the line in the Aiims diagram for a given reaction shows the stability of the oxide as a function of temperature. Metal oxides closer to the top of the diagram are unstable and are easily reduced. As we move down towards the bottom of the diagram, the metals become progressively more reactive and the oxides become harder to reduce. A given metal can reduce the oxides of all the other metals whose lines lie above theirs in the diagram. At the point of intersection of the curves for aluminium oxide and magnesium oxide, A, the change in free energy delta G becomes 0 for the reaction. 2 by 3 Al2O3 plus 2 Mg gives 2 MgO plus 4 by 3 Al. Thus, you can say that magnesium can reduce alumina only below the temperature corresponding to point A. At temperatures greater than 1273 K, magnesium cannot reduce alumina. Further, you can see that the line corresponding to the formation of carbon monoxide is sloping downwards. It cuts across the lines for many other metals. This makes carbon extremely useful as a reducing agent because as soon as the carbon oxidation line goes below a metal oxidation line, carbon can reduce the metal oxide to metal. For example, at lower temperatures, carbon monoxide is a better reducing agent for reducing iron oxide than carbon. Oxide, the ore from which iron to be extracted, is concentrated by roasting or calcination so that water gets eliminated as vapor. Carbonates get decomposed to release carbon dioxide, and sulfide gets oxidized to sulfur dioxide. This concentrated ore is mixed with limestone and coke and sent into a blast furnace to reduce the metal oxide to the metal. Here, coke reduces ferrous oxide to iron, releasing carbon dioxide, as shown in the equation here. This is a combination of two simple reactions. In the first reaction, ferrous oxide gets reduced to iron. Let the change in the Gibbs free energy for this reaction be delta G, FeO, Fe. In the second reaction, carbon gets oxidized to carbon monoxide. Let the change in the Gibbs free energy be delta G, CO. When the two reactions occur, the net Gibbs energy change becomes delta G reaction is equal to delta G CO plus delta G FeO Fe. This becomes spontaneous when delta G reaction is negative. Aims diagrams are useful in predicting the conditions under which a metal ore can be reduced to the metal. It gives information to predict the equilibrium temperature between the metal oxide and the metal. If a graph is plotted for standard Gibbs energy change delta G naught against temperature in Kelvin scale, capital T for both these reactions, then it will go upwards for the reduction of ferrous oxide to iron, FeO, Fe, and downwards for the oxidation of carbon to carbon monoxide, CO. From the graph, you can see that at a temperature above 1073 Kelvin, carbon reduces iron oxide to iron, but itself undergoes oxidation to form carbon monoxide. Thus, the carbon monoxide oxidation line crosses the iron oxide iron reduction line and then remains below it. Let us apply this concept to the extraction of iron in a blast furnace. In the furnace, iron oxide is reduced at different temperatures. Iron oxide ore is introduced into the furnace from the top. At the same time, coke is burnt in the lower portion of the furnace, blowing hot air to produce a temperature of 2200 Kelvin. When the coke burns, it produces carbon monoxide and the heat required for the process. The heat produced moves upwards along with the carbon monoxide. The temperature at the top of furnace is lower, and hence, iron oxides like Fe3O4 and Fe2O3 get reduced to FeO in different stages. This corresponds to the intersection points in the curves which we just discussed. Let us now see how iron oxides get reduced to iron in different temperature ranges. Between 500 and 800 Kelvin, carbon monoxide reduces iron oxides, as shown here. Carbon monoxide acts as a reducing agent since it has a lower negative delta G naught value for the oxidation of carbon monoxide to carbon dioxide than for the oxidation or carbon to carbon monoxide. Thus, in a blast furnace, hematite is reduced by carbon monoxide even though carbon is mixed with it. The equation for this reaction is Fe2O3 plus 3CO gives 2Fe plus 3CO2. In the temperature range of 900 to 1500 Kelvin, carbon monoxide reduces ferrous oxide to iron, as shown here. Silica is an impurity. Limestone removes it in the form of molten slag, which is taken out from the bottom of the furnace. The molten iron obtained in this process contains 4% carbon, along with some other impurities like sulfur and phosphorus. It is called pig iron. Pig iron is melted with scrap iron and coke in the presence of hot air to form cast iron, which contains only 3% carbon. It is hard but brittle. Cast iron is heated in a reverberatory furnace lined with hematite, which oxidizes carbon to carbon monoxide to get wrought iron or malleable iron, the purest form of iron. In this process, limestone is added to remove impurities in the form of slag. The metal is removed and separated from the slag by passing it through rollers. Occurs in combined state as sulfides, oxides and carbonates. Copper pyrites or chalcopyrites and copper glands are its sulfide ore. Cuprite is its oxide ore, while malachite and azurite are its carbonate ores. Now look at the Gibbs energy versus temperature plot for the formation of oxides. You can see that the line for cuprous oxide is almost at the top, while the lines corresponding to the formation of carbon monoxide and carbon dioxide from carbon are much lower, particularly after 500 to 600 Kelvin. Therefore, it is quite easy to reduce cuprous oxide to copper by heating with coke. However, most ores of copper are sulfide ores, and some of them may contain iron. Hence, the sulfide ores are first roasted or smelted to give oxides. The oxides are then reduced to metallic copper using coke. In practice, the concentrated sulfide ore containing iron as an impurity is mixed with silica and heated in a reverberatory furnace. During this process, most of the iron sulfide is converted into its oxide, which further reacts with silica to form a fusible slag of iron silicate. Copper is produced in the form of copper matte, which contains copper sulfide and iron sulfide. The molten matte is now introduced into a converter provided with a lining of silica. A blast of sand and hot air is blown into it. During this process, the remaining iron is removed in the form of slag, while copper sulfide is reduced to metallic copper. The metallic copper then melts and sinks to the bottom of the converter. This molten copper is poured into molds. When the molten mass is allowed to cool down, SO2 gas escapes. As a consequence, the copper so obtained has a blistered appearance. Hence, the product is called blister copper. Blister copper contains 98% copper and is refined through electrolysis. Now let us look at the extraction of zinc. Zinc occurs widely in nature in the form of sulfide, oxide, and carbonate ores. Zinc blende is its sulfide ore, zincite its oxide ore, and calamine is its carbonate ore. As can be seen from the Aiims diagram, the reduction of zinc oxide to zinc occurs at a high temperature than that required for the reduction of copper oxide to copper. Coke is used for the reduction of zinc oxide. Depending on whether sulfide or carbonate ores used for the extraction, the concentrated ore is either roasted or calcined. The zinc oxide obtained after roasting or calcination is reduced to zinc in vertical retorts. In practice, zinc oxide is powdered, mixed with coke and clay, and then made into small briquettes. The briquettes are placed in vertical retorts that are lined internally with clay bricks. Producer gas is used as the fuel to heat the charge. At high temperatures of 1400 to 1500 degrees Celsius, coke reduces zinc oxide to zinc and itself gets oxidized to carbon monoxide. The zinc metal is distilled off and collected by rapid chilling. The zinc obtained is 97% pure and is called zinc spelter. Studied how metals are extracted from their ores by the process of reduction. You know that non-metals are generally available in combined states in their reduced forms. Hence, non-metals are isolated or extracted by oxidizing their compounds. For example, chlorine is isolated by oxidizing brine solution. Since oxidation cannot be carried out by normal chemical methods, chlorine is extracted by electrolysis. The chemical reaction corresponding to the electrolysis is shown here. The delta G naught for this reaction is plus 422 kilojoules. The minimum potential difference needed for oxidation, E naught, is equal to minus 2.2 volts. Due to overvoltage, the electrolysis process requires an external EMF greater than 2.2 volts. In the process, chlorine gas liberates at the anode. Hydrogen and sodium hydroxide are the byproducts. The electrolysis of molten sodium chloride also produces chlorine gas at the anode, and sodium metal is deposited at the cathode. Let us now see how metals are extracted by both oxidation and reduction. You have already studied that of gold and silver are extracted by leaching their ores by cyanide ions. During the leaching process, silver and gold are treated with sodium or potassium cyanide in the presence of air to form the respective soluble complexes. In the process, silver is oxidized to silver plus 1 and gold to gold plus 1. The next step is the recovery of the metals from their respective complexes by reduction or displacement using zinc. In this process, zinc acts as a reducing agent.